Good afternoon and welcome to this Chemistry World webinar. We've got an action-packed hour coming up with three excellent guests, lots of interaction from you and some important take-home messages for you to learn from. So today we're looking at enhancing polymer analysis with comprehensive 2D chromatography. We're going to gain a deeper insight into polymeric structures by leveraging comprehensive 2D chromatography to make better informed decisions and accelerate your materials innovation. Now, there are still people turning up, so I won't tell you any more about the content just yet. What I'll do for now is let you know more about the platform that we've chosen to use and how you can use it to interact with our guest speakers. Now, we have chosen to use GoToWebinar today. It may be familiar to you. There's been a lot of webinars happening over the last few months for obvious reasons. People are working from home more. But if it's not familiar, then do spend a minute or so now just getting familiar with the GoToWebinar bar, which is probably down one side of your screen at the moment and has the various different options that you can use to control your presence in the webinar, and most importantly, to control how you ask us questions. So there's probably a questions box down at the very bottom of the GoToWebinar column. You can use that to send messages to our speakers and ourselves at any point throughout the webinar. So if there's anything that somebody says you're not quite sure about, you'd like them to expand on, you'd like to know how that could be applied to your own area of work, then just get those questions in straight away. We'll have plenty of time for Q&A at the end of the session, but also we keep a record of all of the questions. So that not only helps us to make sure the next webinar is even more appropriate for you and contains all the more facts that you need, but also if there's something that our speakers can get back to you by email about, then they will be happy to do so. So get those questions in at any point throughout the webinar as we go through. So that's GoToWebinar. We'll also have some polls because we're really keen to get to know a bit more about you. So when those polls come up, all you need to do is click on the answer that you want to share, and we will make a note of all of that. You'll see how you compare to everyone else. You may find that it doesn't always take the answer first time round. That might be because you've got things in full screen. That seems to vary on what type of machine you're using. So if you find it doesn't take the answer straight away, just pull that window out of full screen, try again, it should be fine. So that's GoToWebinar, that's how you interact with us. And now let me tell you a little bit more about what we've got coming up over the course of the next hour. So once again, enhancing polymer analysis with comprehensive 2D chromatography. By the end of this hour, you will have learned how to increase your sample throughput and the efficiency of your laboratory operations by obtaining accurate and importantly repeatable sample preparation. You will also learn the best ways to leverage comprehensive 2D chromatography to gain additional insight into complex polymer analyses, and you'll learn the most suitable ways that advances in 2D technology can be applied routinely to support your daily polymer innovation needs. Now, this webinar is brought to you in partnership with Waters. You may have also seen our precision polymer analysis collection on chemistryworld.com at the moment. Waters have been fantastic partners with us for looking into this world of polymer analysis. They make the equipment that you can use, but they also have wonderful support, great documents and advice on how to make the most of the analysis that you're doing. So we're really pleased to be partnered up with them, and they found us exactly the right people to speak to about this so that you can ask really good questions too. Now, with that in mind, there are 3 handouts that are currently available in the GoToWebinar panel. Just click on those handouts and they will open in your browser. You don't need to read them during the presentation, but they may be really useful afterwards to further your learning. So just click on those when you have a chance, load them up in your browser and have a look later. So those handouts, we'll refer to them as we go through the presentation, but you may as well grab them now while I'm waffling about GoToWebinar. Now, next thing I'm going to do is introduce our 3 speakers. So the 3 speakers today are Jennifer or Jenny Bain. She's Market Development Manager for Material Science at Waters Corporation. She spent several years in academia working on various government and military funded projects in the fields of polymer chemistry, material science, nanotechnology, and biotechnology. So well-rounded experience and a very good person to have with us today. After her, we will hear from Daniela Herd, who's a polymer scientist for PSS Systems in the Software and Solutions Department. She studied chemistry at the University of Mainz in Germany, and after achieving her PhD, she started working for PSS, and then in 2005, she moved into the marketing team where she's responsible for education and customer training. So any questions about this, she's the right person to put them to. And finally, after that, but certainly not lastly, Claudia Loman, who is a senior scientist in chemicals and materials science at Waters Corporation in the US. Her area of focus is polymer characterization by advanced polymer chromatography. That's APC. We'll be hearing a lot about that coming up, and method development. She also works in customer support and in 2D chromatography, so fits our topic wonderfully. So a huge thank you to Waters for finding our three guests. Big thank you to Jenny, Daniela, and Claudia as well for joining us. Before we hand over to Jenny to pick up on the first part of this presentation, I should let you know that everybody who has attended the live broadcast will get a certificate. It's our way of saying thank you for joining us for the live event. And also, if there's any aspect of this that you miss, that you'd like to go through again, we will send you in a couple of days' time a link to the recording of this webinar. So you'll be able to watch that again at any point in the future. So don't worry if your doorbell rings or your telephone rings, you can come back to pick that up later. Now, before we really go into the topic, we're going to get to know a little bit more about you. So the next thing we're going to see is a poll, and we'll find out what your experience is. So our first poll, and do just click one of the three answers that best suits you. Are you currently using GPC/SEC? So please select, is it yes, you're using it, but in organic solvents, yes, in aqueous solvents, or no, you've never used that technique before. This will really help us to know who it is that we've got in the audience today. It'll help us to tailor that content, and we will have a better idea of how to make sure that this webinar is as appropriate as it possibly can be. So we'll give you a short while to vote in that, and I can see the votes as they're coming in. Interesting balance so far. And for all the people who've arrived in the last couple of minutes since I started, the most important thing here, grab those handouts while you can, and get your questions in. The Q&A box, the questions or chat box at the bottom of the GoToWebinar panel is how you can interact with our three speakers and really make the most of today's webinar. I think that's probably enough. Most of you have voted, over 3/4 of you have voted now. So let's have a look and see the results. So there we go. So 20% currently using these techniques in organic solvents, 13% in aqueous solvents, but the majority, almost 70%, 68% of you not used this technique before. So certainly a learning journey ahead of you. Now what we're going to do now is hand over to Jenny. So I will hide these poll results, and we should see Jenny's screen very soon. We're going to turn the webcams off throughout the presentations, but we will turn them back on for the Q&A. So you do get to see who you're talking to as we come into the Q&A aspect. But while the presentation's on, we'll turn the cameras off. So Jenny, hopefully we will be able to hear you as well as see your screen. Let's just make sure that you are not muted. There we go, that looks good. Jenny, thank you very much for joining us. I can hear you now, yes.
Good. And I'm hoping you can see the right screen, which is...
we can see the PowerPoint presentation now. So thank you again for joining us. Interesting results, that 68% of the audience not used this technique before. I'm sure that by the end of this, absolutely every one of them will want to, and they'll see the value of it.
Hopefully. Hopefully we don't baffle you with science, excuse the pun. But yes, any questions that you have, obviously ask one of the three of us at the end. We're happy to answer even the most basic questions.
Excellent. Well, thank you again for joining us. I'll sit back now, let you get on with it. So I will pop back for the next poll as we get to learn a bit more about our audience just before we go to Daniela's presentation. So I will see you all later on. Thank you for joining us.
Okay, so as Ben has kindly introduced us, I won't bother doing that. And as Ben said, thank you for attending today to learn more about comprehensive 2D polymer chromatography. So we're starting at the advanced end of polymer separations and chromatography in general. But as I said, hopefully we don't baffle you. And luckily we're starting with a slow introduction of where this is relevant. And the numerous ways it could potentially help your polymer analysis either now or in the future. So we're hoping that we can shed some light on what many presume to be the niche end of polymer chromatography, and how it's already got some relevance, but it has growing relevance in an ever-changing polymer industry. So as I said, I'm going to get us started and walk us through the relevance of the technique, and then I'm going to pass you over to the real scientists for the more exciting stuff. So separation technology in general, so you may have heard of GPC, gel permeation chromatography, or sometimes it's called SEC, size exclusion chromatography. In general, for those of you who don't know, is the separation of polymers similar to LC or HPLC, which you may have used for small molecule analysis, but based on the hydrodynamic size, so the general size of the polymer. And high resolution separation techniques can apply anywhere, not only in what we think of as the stereotypical polymer industry, but all across the chemical and materials industries, and even into pharmaceutical and clinical industries for some applications. So depending on those applications, it can have relevance in the design of medical devices, in extractables and leachables analysis, in the oil and petroleomics industry, and then particularly in things like production of sustainable materials, green chemistry, high performance materials, and our traditional kind of bulk and commodity polymer synthesis and analysis. Essentially, any polymer R&D setting where traditional SEC doesn't tell you maybe enough about your sample. So I probably should mention that for those of you who don't know, GPC or SEC gives you a molecular weight value for your sample, and this is based on a calibration against a known or similar standard to the polymer that you're looking at. And then it gives you a relative molecular weight compared to that standard, so you know how big the polymer is that you've synthesized essentially. But it doesn't always tell you enough about the polymers that you are looking at. And the polymer analysis world is becoming ever more complex, as I've just said. So I'm sure you're thinking, if that's the situation, that synthesis is becoming more complex, products are becoming more complex, why on earth make life more complicated by making your analysis complex? So by going from, say, a one-dimensional LC or SEC type separation into a more complex, as it's perceived to be, two-dimensional chromatography separation. Well, hopefully we can show you the benefits of why you would want to do that. So I'm probably slightly stating the obvious, but as technology in all markets becomes more advanced, we need a wider range of analytical techniques to effectively characterize the materials that go into the familiar products that we see across many markets, as I've mentioned a few of them already: the bulk chemical industry, the automotive industry, aeronautical industry, and throughout the supply chains that support the production of those products. The diversity of R&D today, focusing on polymer applications and those associated with polymer applications, is working towards creating the kinds of products that I've just mentioned, and has veered along the way from bulk linear polymer production, things like polystyrene production, to the kinds of products where these polymers alone are not enough to be able to make the products that we're talking about. So as R&D starts to explore more complex polymer architectures, things like block copolymers, grafted polymers, dendritic architectures, amphiphilic materials, I could go on and on and on, but the kind of structures that you're seeing in that cartoon in the center of the screen. And then we factor in blending these polymers or adding in associated additives in the case of many kind of master batch product formulations. Standard GPC or LC alone doesn't always give you enough information about the polymer structure and, more importantly, its predicted properties on a bulk scale. So to answer the swathe of questions that tend to go along with producing these types of products, which you can see here, while ensuring things like safety and reproducibility are maintained, a wider range of analytical techniques are often needed. So, for example, for fundamental structural analysis, you might need, say, GPC, NMR, IR analysis, even things like Raman spectroscopy, as well as maybe thermal techniques. And then once we get up to the bulk type properties, you might be looking at surface techniques to fully understand the picture of what it is you've made and the properties that go along with that product. And one of the more advanced techniques that's becoming more prevalent in this type of analysis is multidimensional or 2D chromatography, which is obviously what we're here to talk to you about today. So chromatography allows us to measure the distributions of the polymers that we're looking at, and multiple distributions requires multiple separations. So we're not claiming that chromatography or 2D chromatography alone can answer all of these questions, but the more information that you can get from your chromatographic analysis, then possibly the more you can cut down the analysis time or the amount of techniques that you have to throw at that sample to really understand what's going on. And the faster you can innovate, the faster you can answer some of those problems that we all know go along with synthesizing polymers. So I hope, based on the poll results, that I've not gone too far too fast. So we now know that SEC or GPC is a generally accepted polymer separation technique that gives us a molecular weight distribution in its very basic terms. So by means of an introduction to 2D chromatography, and this will be explained in greater detail by my colleagues later on, 2D chromatography essentially combines two independent separation techniques into a single analysis. So if we look at this example on the left with the blue and yellow polymer chains, if we take this to be what we can describe as a relatively complex polymer sample, and I'm using air quotes, that's open to interpretation how complex that polymer sample would be, but essentially something that contains multiple chain lengths and several varying compositions. So you can see there you've got some block copolymers, you've got some mixed polymers, you've got some polymers of a single composition, and they're all mixed in together, either in a blend or just by pure accident, which I can vouch for the fact happens regularly. So if we look at something with multiple chain lengths and varying compositions, an analysis of this type of sample with what we class as standard GPC type separations, our results are likely to be hindered to some extent by what we call the polydispersity of the sample. So the more stuff we've got in there, the wider the distribution of the peak that we'll get in our chromatogram, and the less information we'll really get from that chromatogram in what's considered a generally low resolution traditional GPC technique. When we combine these traditional GPC techniques, or ideally a high resolution GPC, so something like, as Ben has already mentioned and as Danny and Claudia will talk about more, something like the APC or the Advanced Polymer Chromatography system, and we take that analysis and we combine it with the second dimension. So in our second dimension, separating by something like chemistry, so kind of a more HPLC type method that you might be more familiar with, we combine those into what we call 2D chromatography. So that's what you can see in that graph in the center. So then we are separating by both the polymer's composition, so that's on the y-axis in that graph, and by its hydrodynamic volume, which I mentioned earlier, which is essentially the relative size of the polymer. And we combine that into the same analysis. And this is how that's shown in its most basic cartoon form, and you'll see the real data towards the end of this presentation. But essentially we're seeing that what looks like separation by composition only, we only see maybe 4 or 5 species, and by size only we see maybe 4 species. When we combine these two analyses, we can see that in actual fact we have a lot more in that sample that we can see by looking at those two analyses independently of one another. So why do we need it? So understanding macromolecular structure is fundamental to the use of polymers. Polymers vary in molecular weight, chemical composition, end groups, architectures, and heterogeneity of polymers makes separation incredibly difficult, especially when you're looking at things like copolymers or graft polymers. And 2D chromatography provides an ideal alternative to analyze those really complex polymers. As you can see from that graph, it improves both separation selectivity and peak capacity, and we start to see what I like to call the unknown unknowns that you didn't know were there. So the challenges, but that paired with the challenges in separation of polymers are, as I said, only compounded by the complexities of the polymer R&D world today. So high performance polymer research, things like green or sustainable chemistry, which is coming more to the forefront, the idea of new and innovative polymer structures becoming more prevalent, people looking at things like biodegradable polymers where you really need to interrogate your samples, and generally the emergence of what we class as high performance materials, where you really need to control those bulk properties, as well as the practical side, so the reduced consumption of resources, things like solvents, analysis time reduction, and general waste. We're all moving towards a greener, more sustainable world, not outside of, in the world generally, but obviously within the lab. We're not known for being the greenest of industries. But when we try to combine these types of materials with legacy analysis, it can sometimes hinder our progress. So legacy GPC can slow down getting new polymers to market. Existing column technology, particle sizes that are generally used in GPC or LC systems can limit characterization by increasing dispersion, and gaining a competitive advantage can also be compromised. Using multiple techniques to analyze a single polymer results in large data interpretation, which I'm sure you're aware of, which is complex, time-consuming, and so these two things aren't always complementary. So the changes in the polymer world and the legacy technology can sometimes butt up against each other. And as I said, slow things down, raise more questions than it answers, sorry. So using 2D separation techniques can overcome many of these limitations of GPC. So in some of the more complex analytical scenarios that we've discussed, for the right sample, it can vastly improve on getting a polymer's molecular weight distribution information and provide additional information to better inform either your next analytical or synthesis step, depending on the sample, and it has the potential to improve on things like degree of structural resolution, information about functional groups, amphoteric behaviour, even zwitterionic behaviour, and general conformational information. But is it not, as I said earlier, is it not easier to perform these two analyses independently? So run your GPC or your SEC and then run your LC and have a look at them. Well, the short answer, unfortunately, is no. If separation by molar mass and separation or molecular weight and separation by composition are performed independently, it's not always possible to gain complete information and two entirely different products can give the same one-dimensional chromatogram, and then we only spot the heterogeneity when we run a 2D separation. And we look at things like a contour plot, which is shown on the right, which I won't go into because the others will talk more about that shortly. So what makes Waters and PSS qualified to call themselves experts in 2D separations? Well, I'll quickly talk you through the Waters side, and then I will hand over to Danny to tell you all about PSS. So Waters Foundation is based on separation technology. Back in 1963, Jim Waters, along with Dow Chemical Company, essentially came up with the first GPC via the column technology. And then 2 years later, a key paper by Moore coined the term GPC, and the separation technique was essentially born. Since then, we've been built on general separation techniques, so LC, GPC, and then in 2004, Waters unveiled what you may have heard of as UPLC or UHPLC technology, which was a seminal moment in separation history, separation history, with which had a positive impact on LC separation and lab life in general for those who were doing small molecule separation. In the HPLC world, HPLC is considered the same as GPC, so a relatively low performance technique in comparison to UPLC. And as we compare from one to the other, so as we go from left to right with our products, and obviously with the equivalents from whichever company you may buy these products from, we all have the same equivalents. We go from HPLC up to UPLC, and generally speaking, that means smaller particle sizes and lower system dispersion, which results in faster, higher resolution separations. This is because of increased operating pressures, reduced flow rates, smaller particle sizes, smaller column diameters, and the result of that means that you get faster separation, you get less dispersion, so you can see in that dispersion impact box you're getting a much sharper peak, and the general cost per sample, generally speaking, depending on obviously specific labs, is reduced because of the shortened analysis time, etc. And that's the analysis of small molecule analysis with UPLC technology. But what about the big stuff? Obviously, this is a polymer webinar, so I want to speak about polymers. So back in 2013, Waters transferred UPLC technology into a dedicated polymer system. The advanced polymer chromatography system, as we've mentioned, was born in 2013. And that transferred the technology over to polymer analysis. And then this year we've joined forces officially with PSS to combine that high resolution separation with dedicated 2D software and expertise. And on that point, I will hand you over to the expert on 2D separation, Danny, to tell you more about PSS and the finer details of 2D chromatography. Thank you.
Thank you very much, Jenny. Just before we hand over to Danny, just in case you weren't here at the beginning, our second guest for today, Daniela Herd, is polymer scientist from PMS Systems in the Software and Solutions Department. But before we hand over to her, we're going to find out a little bit more about you, the audience. And so our second poll question of the day, you've been through one of these, so you know exactly what to expect. Have you used 2D, two-dimensional chromatography before? Yes for LC, yes, but only for GC, or no? Let's see what sorts of results coming in. So if you've never used GoToWebinar before, you may not be familiar, but I see a running count of who has voted and what they have voted. And it's always, I find, really interesting to see how these things change over time. But right now, I have to say the people who've used GC haven't turned up for this webinar very much, and it's predominantly LC or people who haven't used it much at all. So if you have used 2D approaches, with GC, only for GC, then make sure you get your vote in and make sure you get yourself represented in these results as they come through. So I'm going to give it a little bit longer to let everybody vote. And now is a good time for me to remind you to get your questions in. The chat box at the bottom of the GoToWebinar panel is where you can send a question to any of our panelists. If there was anything Jenny said that you would like a bit more clarity on or a bit of expansion with, just fire in a message. I can see already we've had good questions from Amber Assen, from Sunit, from Raja Kumar, from Iman, from Arnab. Lots of good questions coming in. So do please keep your questions coming in. Don't wait until the end. Get them in as soon as they occur to you throughout the webinar. So I think that's probably just about enough time for people to vote in the poll. I'm going to share those results now. And so 18% of the audience have used 2D with their LC approaches, 9%, half as many, have used it only for GC, but 73%, most people haven't used these approaches before. I'm sure you'll have seen, we're only a third of the way through, and I'm sure you'll have seen already what a powerful technique it is and why it may be something you want to explore for the future. And any questions, as I said, get them in. That's quite enough for me. Daniela will be our next guest. So she studied chemistry at the University of Mainz in Germany, got a PhD in physical chemistry back in 2000, and since 2005 at PSS, she has been responsible for education, customer training. She knows these techniques inside out and knows how you can make the most of them. So we'll hand over to Daniela now, and let's see, hopefully we will be able to hear and see her shortly. So that's Daniela's screen. Excellent. Daniela, thank you very much for joining us.
Hi, Ben. Thanks for letting me be here. It's really nice to see that, and really nice to see those interesting poll results. So thank you for sharing that with us. I have to apologize to those people who already used 2D for being a little bit more detailed about how we practically would set up such a system. However, I think it's important that all of us understand how we create such a counterplot, because Claudia will use them for her applications and will show some applications. And I think it's important for all of us to understand how these counterplots were really produced. So
it's always good to understand the history, isn't it? Okay, I'll leave you to it now. Thank you very much. Just before I go, another quick reminder, those handout resources, the 3 PDFs you can download, grab them at any point. You don't need to read them during the webinar, but they will come in handy later. Thank you again, Daniela. I'll leave you to it.
So thanks. Jenny has walked us through the ever-changing needs for modern in-depth characterization of polymers and for Waters' invention of GPC. As my company, PSS, is solely focused on the elucidation of structure-property-function relationship of macromolecules, I can surely say that GPC is one of our key technologies. Founded in 1985, PSS was and still is dedicated to liquid chromatography of macromolecules. Our goal is to develop true solutions based on easy to use and on reliable products, and we need to include the latest findings in material science. So besides analytical services and reference materials and columns, software is one of our key products. And from the early beginning, PSS developed software first, like in 1988, for Atari platform, a platform which I assume our younger audience would not even recognize, and since 1992 for Windows platform. Already in 1995, PSS released the WinGPC software module for two-dimensional chromatography. And in the following years, we added more and more solution to increase the usability of 2D so that more labs can profit from the advantages of that technology. All enhancement had the basic idea to allow for faster, for more precise and more meaningful results. And the latest addition in 2020, which we will talk about today, was adding the full support for the Waters APC system to the WinGPC Unichrome Chrome pilot. So The PSS and water's history is both interesting and consequent. As companies, we do have a long-standing relationship, and we joined forces, as Jenny described already. We joined forces here with a common goal to make two separations as fast, as environmental, and as user-friendly as possible by bringing together our expertise. So how could such a solution from PSS and waters look like? Will a 2D system, specifically one for comprehensive 2D, because is that what we are trying to do, be more complex or be even too complex? I'll let you decide. Let's have a look at this picture here. I think a first look at the picture here in this corner shows that the required components do not look too scary. We see here already a 2D system with a very small footprint, which allows already to perform two different kinds of separation. Let's start with the bottom right instrument, the QSM, the Quaternary Solvent Manager. This is a low pressure gradient pump allowing us to do gradient separation. On top of it, we see the FTN, the flow-through needle sample manager or auto sampler, followed by the CMS, the single zone column manager, which is housing the column for the first separation. The components here on the left-hand side are the isocratic solvent manager at the bottom. Again, a CMS, single zone column manager, what we see here. And at the top, we see a photodiode array detector, a PDA, being capable to measure UV traces and spectra. And both dimensions are connected by one single high pressure transfer valve that unifies two single separations into one comprehensive 2D system. So here we do see the same setup, but with a better chance to understand the fluidic connections and how the valve is equipped and operating. The valve itself is, I mentioned that already, a high pressure valve. It has 8 ports and it has installed 2 loops of equal volume. In the beginning, one loop, in this figure, the blue one, is connected to the separation column of the first dimension, which is typically an HPLC column, allowing for separations based on the different chemistries in our sample. The second loop, the red one, is in between the isocratic pump and the GPC column, which is used to separate based on the size of the molecule and thus most probably the molar mass. We have then installed, after the GPC column, the detector, which provides the data required for the 2D analysis. So how will this setup now become a solution for a comprehensive 2D, and how can we create such a nice counterplot Jenny has already shown and Claudia will explain more later? First of all, it's important to understand what comprehensive means. In comprehensive 2D LC, the sample containing effluent of the first dimension is fully sampled, which means we won't ignore any sample parts. We'll just re-inject everything. The definition of comprehensive requests also that at least equal aliquots of all fractions are transferred from the first to the second dimension. Furthermore, it's expected that the resolution from the first dimension is maintained. Theoretical considerations show that around 2 to 4 cuts per peak are necessary to fill this. So this means that for the sample analyzed on the first column here, that for these samples, we need to collect and inject fractions or a lot of different fractions onto the second column. We achieve this by constantly switching the valve once one of the loops is filled with effluent from the first dimension. I think a short animation will help us here to understand the principle a little bit better. Starting position is that loop number 1, the blue one here, is connected to the HPLC column and filled with effluent. Once the loop is filled, the valve is switched so that the isocratic pump here is now injecting what is inside loop number 1 on column number 2 and this will result in one GPC trace. Meanwhile, loop number 2, the red one here, is filled again with effluent from the first dimension. Again, once loop number 2 is filled, we will switch back so that now the isocratic pump is connected to loop number 2 again and is injecting the content of this loop onto column of the second dimension. And again, this will result in a GPC trace. So now the valve is continuously switching back and forth so that we obtain a large number of GPC SEC chromatograms. You see here, with every switch, I inject onto the column and I create a new chromatogram of the fraction which had been separated on column number 1 before. So after we have collected all of these fractions, we can then combine the counter plot from these data, and Claudia will show some nice plots with real data later and explain how to interpret them. So now, after having seen how a comprehensive 2D solution can be operated, we have to talk a little bit more about the details. In GPC, columns are the heart of the system. In 2D, besides the valve and the software, the second dimension columns make a difference. The launch of the Waters BEH columns was exciting for all of us 2D pioneers, as these columns offer some advantage for 2D separation. First of all, in comprehensive 2D, we need very fast and high resolution GPC in the second dimension, as we want to analyze so many fractions and don't want to lose too much time or too much resolution in that. This reduction in analysis time is extremely beneficial when using the BEH columns. In addition, the higher pressure stability allows us to work at very, very high flow rates when using the columns, resulting in even less time required. The high resolution and the small dimensions additionally allow us for solving savings, and we have a very nice example of that later. In addition, there is one thing which also needs to be considered. As we do directly inject the effluent of the first dimension, which is normally that of a gradient separation, it is very practical when the second dimension column can withstand many different solvents, as this is the case here. Another key element that makes a real difference is the software for comprehensive 2D. I mentioned earlier that PSS has developed software from the early beginning. While this has not changed, the role of software in the lab has definitely changed. In the beginning, software was just there to acquire data or to calculate results so that we users don't have to do the mathematical operations. Today, software is more used to manage the complete workflow in the lab, to control and monitor instruments, and to allow for analyzing large amounts of data. So this was, of course, also the goal for our WinGPC software, so that we rather supply our users with MCDS, a macromolecular chromatography data system, than with just the software. Important to know about WinGPC is that it's designed for macromolecules and that it's designed to handle the distributions or the multiple distributions that can occur or that will always occur in polymers. WinGPC comes in 3 editions. 2 of them, the multi-workstation and the client-server edition, offer manufacturer-independent data acquisition and fully support the comprehensive 2D solution. There are specific WinGPC software modules available for all tasks in macromolecular chromatography. You can basically group the modules in modules for mass and structure analysis. For example, you see here the light scattering modules, which are a famous example here. We do have modules that ease your life, like for example, the compliance pack for 21 CFR compliance or the report designer. And we do have a group of copolymer analysis modules. This is where the 2D software module belongs to. So what is new for this new comprehensive 2D solutions that we've just shown in the previous slides? The additions that have been done were mainly applied to the ChromPilot and to the guided 2D valve setup. The WinGPC ChromPilot is our module for the manufacturer independent instrument control. We use RC.NET driver technology for this and include and develop drivers so that all instrumentation in the lab can be utilized using just one software package. Basically, all instruments shown here on the left-hand side of the instrument configuration manager, all of them have their own driver in the background. And in 2020, we added newly developed drivers for the PSS high pressure transfer valve and for the Waters APC components, so that now you can combine these elements in your 2D configuration and you can connect to your comprehensive 2D system. The guided 2D valve setup is there to guide you through the process in planning your 2D runs so that you can absolutely concentrate on the chromatographic part rather than on handling of instrumentation or a system. Here you see step 2 of the setup. After loading the methods for each dimension, for dimension 1 and 2, you enter here the chromatographic parameters such as runtime for the first dimension, runtime for the second dimension, and how many transfer injections you want to have for each sample. The valve initialization and all valve control during the complete runs for all of your samples that you have scheduled here is then automatically done by WinGPC. So valve control is taken care of by the guided 2D valve setup, but what about the other components? On this slide, I just want to share with you the simplified user interface of the WinGPC ChromPilot. We connected here a system similar to the one that of the applications that Claudia will show in a minute. In this simplified UI, you can access all important parameters for convenient operation of all components at once. For example, you can define here upper and lower pressure limits. You can also set end action so that the system is automatically shut down after you have collected the run for all of your 2D samples. You can also save the instrument methods here for each dimension if this is required, so to make life easier for you and your colleagues if you use the techniques or the separation techniques more often. So with this information, I could hopefully show you how a comprehensive 2D solution looks like. I could hopefully show you how to do that in a user-friendly way and how a 2D counterplot can be generated. And with this, I would like to hand over to Claudia so that she can share some nice examples and results with us. And she will also elucidate the data analysis capabilities of the WinGPC 2D software module.
Thank you very much, Daniela. So before we hand over to Claudia, we've got our third and final poll of the day. Once again, do keep those questions coming in. We've had lots of great questions so far, but now is really an excellent opportunity for you to speak to 3 experts in the field and really get the answers to the questions that you want to ask. So our third and final poll. Do you have experience with interaction polymer chromatography? Now, simple yes or no answer this time. And once again, I'm seeing the answers as they come in. And whoever was first to say no was very quick off the mark there, but things are balancing up as we go through. So again, I'll give you a short while to make sure you get all of your potential answers in there. And this is a good chance to type up those questions that may have occurred to you while listening to Daniela's presentation. Thank you, Daniela Herd, second of our 3 guests for today. Next, Claudia Loman, Senior Scientist in the Chemicals and Materials Science area in Waters Corporation in the US. Her focus is on polymer characterization by APC, advanced polymer chromatography, and in method development, as well as customer support and 2D chromatography. So we'll hand over to Claudia in just a second once we've given you enough chance to vote. I think that's probably enough of you. This takes a snapshot of our audience, and I shall share those results. There we go. 82% has no experience with interaction polymer chromatography. You're in the right place to learn more about it, learn more about its potential benefits and how it might be a useful thing for you to move into in the future. And the 18% who already have are clearly here to learn more about something they already know and love. So thank you very much for filling in the poll. The next person we're going to hear from, I'm going to hide this down. Next person we'll hear from is Claudia Loman. So Claudia, if we can open up your microphone and share your screen, then we can pick up from there.
Yes.
And we can hear you. That's a very good start.
Okay. So.
And we'll just need to see your screen as well. Perfect. There we go.
Okay.
Thank you for joining us, Claudia. Two strong presentations to follow, and I'm sure you can take us up to the finish line in style. So I will leave you to it, and we'll speak to you again for the Q&A session after your presentation.
Thank you. And I will now round up the this webinar with some data. So after Jenny and Daniela covered what the capabilities of APC and WinGPC are and what they can do for you, I would like to walk you through some examples. In this example here, a polymer blend consisting of 8 polystyrene and polymethyl methacrylate samples was separated. So you might ask yourself, what are the first steps? How do I go about developing a method When starting method development for a 2D method, you run both dimensions individually to get an idea how many peaks you get and where they elute. In this case, study, SEC was done first to separate on 2 separate detectors. Detectors have different selectivities. One detector can reveal something that the other that is invisible to others, as you can see in this overlay chromatogram. The LSD trace shows a shoulder in the middle peak, which is not present in the UV trace. The UV trace picks up an additional small peak that does not appear in the LSD trace. If you have ELSD and UV, it's worth running both of them. Obviously, if your sample is knowingly not UV active, then you have to use the ELSD. In the case at hand, the main peaks are well baseline separated, but there are also smaller spikes and peaks that are appearing. But you only see a few peaks. The next step is the gradient separation from chloroform to THF. Again, you see 3 main baseline separated peaks and 2 smaller ones. Both detector traces differ slightly. There are 5 peaks detected in the SEC run, with some irregular peak shape. The gradient run also reveals 4 to 5 peaks and spikes. There are still a few peaks missing. The individual size-based separation shown previously and this gradient separation suggest that there could be more than meets the eye. But if this blend is re-injected with both separations run consecutively, then the result looks different. As mentioned before, the results are plotted in a contour plot. In this plot, the elution time/volume of the gradient run on the y-axis and the elution time/volume of the SEC run is shown on the x-axis. Next to the y-axis, as you can see, go back. Next to the y-axis, you can see the individual gradient result, and on the x-axis, the individual detector trace from the SEC separation as a references. The boxes around the multiple populations denote fractions that eluted simultaneously. The vertical boxes indicate where separation by size has occurred. So polystyrene and polymethyl methacrylate of similar hydrodynamic volume coelute in the SEC run by itself. The horizontal boxes show a separation by chemistry. There is an excellent separation between the two chemistries. Since the PMMA samples are not on the polystyrene samples are not on the same level as the PMMA samples, it can be reckoned that a slight molecular weight influence was occurring during this gradient separation. Under these conditions, you see all PMMA molecular weights coeluting, PMMA fractions coeluting in the gradient run, while the polystyrene fractions are slightly shifted. Polystyrene elutes here in SEC mode. And there has been quite, as you can see, there has been quite a bit of coelution going on in both individual dimensions. So, long story short, by combining a separation by chemistry and by size, you can increase the separation capability. Now you can see 7 peaks instead of the 4 to 5 with spikes and shoulders, as you have seen in the previous slides. The 8th fraction is coeluting with another fraction because the separation range of the column was targeted on the molecular weight of the medium fraction. But nonetheless, 7 out of 8 is very good. So here are the stats. As for the solvents, nothing too fancy. Runtime in the second dimension is very short, with under 3 minutes and with high resolution. What I also like to point out is that the total separation has been completed in under 2 hours. A 2-hour runtime is normally on the quick end of what you can expect. Usually, the total runtime ranges from 2 to 4 hours for comprehensive analysis. The total solvent consumption is less than 250 milliliters for our metric calibrated audience. For all others that are more familiar with imperial measures, it is a bit more than a half US pint. With a non-GBC setup, the total solvent consumption would be considerably higher. So, sticking with the same well-known starting compounds, polystyrene and polymethyl methacrylate, I would like to show another example where 2D analysis reveals more than what meets the eye in a single dimension. This time, we are not targeting a blend of neat compounds, but we are working with a copolymer style graph polymer. The backbone consists of PMMA and the side chains of polystyrene. Both graph polymers derive from syntheses that were conducted under different conditions. Just as with the previous example, the analytes will run on both individual dimensions. On the left-hand side, you can see the overlaid results of the SEC analysis. Both graph polymers yield a bunch of peaks that are not baseline separated. Three peaks in total for both. Due to the difference in the overlaid traces, it is apparent that the composition of both graph polymers is different. On the right-hand side, you see the overlaid ELSD traces from the gradient analysis. IPC stands, as Daniela already pointed out, for interaction polymer chromatography. It is an overarching description for interaction-based separations, as these come in different varieties, which can all be incorporated in 2D analysis. Again, multiple peaks for both graph polymers. It seems that sample B yields a slightly better separation than sample A, knowing that the synthesis strategies were different. Unreacted side chains or backbones could still be present. Both techniques performed by itself yield insufficient information. But yet again, 2D analysis yields a different view of things. Not only have the peaks become more colorful, you can also see that additional peaks surfaced. On the left-hand side for sample A, you can see three main peaks that you saw before. For sample A, you can see the three main peaks that you saw on the previous slide, but there are also some thin yellow lines that might be difficult to make out. These small fractions co-eluted in the one-dimensional run. The fraction eluting at the top, it is around 7 milliliters elution volume. On the y-axis is unsubstituted backbone. The fraction on the lower left-hand corner in the is the target polymer, the graph polymer. Right next to the graph polymer fraction, there is a separate fraction consisting of unreacted side chains. By looking at the overall results of sample A, it is apparent that the synthesis strategy is different to that of sample B. Although an individual one-dimensional trace of both samples were similar, the 2D result of sample B differs greatly from that of sample A. In the top half of the right chromatogram, there is a large fraction of graph polymer with different grafting densities. In between, there are some mixed fractions. Just like with sample A, there is also a fraction of unreacted side chains present. After improving the separation going from 1D to 2D separation, you might ask yourself, is that all the information I can get out of the 2D experiment? A bunch of colorful blobs? The answer is no. As Daniela already lined out, WinGPC is a powerful tool with lots of potential. You can get more information out of this. I'm sure you already asked yourself if you can get more, if you can get some molecular weight information out of your 2D experiment. Your way of reasoning could have been, if I do size-based separation in the second dimension, I should be able to get molecular weight. Besides, the main reason why I do GPC, SEC, or size-based separation, or whatever you like to call it, is molecular weights. And I agree, you are absolutely right. So this is how you do it. The process is pretty much the same as if you make a one-dimensional measurement. Obviously, you have to calibrate the second dimension. You inject an ample amount of polystyrene and or polymethylmethacrylate standards to cover the full separation range of your column. You define the baseline and integrate your standard peaks. By zooming in on the peak apex and assigning a molecular weight, WinGPC generates a calibration table. At the same time, in a separate window, a calibration curve is created. Here you can see an example of a textbook calibration curve. Exclusion limit and permeation limit is nicely visible. The standards can be run beforehand just on the second dimension, saving overall runtime. Coming back to the contour plot of our graph polymers with the starting materials but differing synthesis strategy, and having calibrated the second dimension, it is now possible to assign a molecular weight based on the calibration to every elution volume in the second dimension of the contour plot. But you can do even more than this. You can select your fractions of interest by drawing a grid. It doesn't always have to be a circle around the respective fraction with your mouse. For these fractions, molecular weight calibration curves can be assigned so that you now get the complete molecular weight information. Here are the results are shown here on this slide. Please note that the x-axis here is no longer the elution volume from the second dimension, but it is molecular weight in log scale, as you are used to from your GPC results. Slight shifts of the peak compared to each other are observed as polystyrene peak 1 and PMMA peak 2 are evaluated with matching calibration curves. This means that a calibration curve constructed from narrow polystyrene reference materials was used for all fractions of the polystyrene peak, while a calibration curve constructed from narrow PMMA reference materials was used for all fractions of the PMMA peak. The numerical results for the peaks defined using the grid are shown in the tables below. Knowing that the graph polymers are sort of copolymers and having all those nicely separated fractions, you might ask yourself, is there a way of determining composition? Can I get even more out of my 2D experiment than superior separation and molecular weights? Yes. This has not been done with this particular analysis, but it is generally possible using the chemical heterogeneity module of WinGPC. This module allows constructing a calibration curve with standards of known composition, and I emphasize this. We're not talking about molecular weights. It has to be a known composition to determine skew and width of a compositional distribution. If this calibration is assigned to the first dimension this time, the elution volume axis here will be replaced so that it is possible to determine the amount of, for example, PMMA in a fraction. So here's a quick summary of what you have to consider when doing 2D chromatography on polymers. Before you even get started in the lab, look at your polymer. What information am I trying to find out? Am I just doing a sample or batch-to-batch comparison, or do I want detailed distribution information? If you decided on the latter, then you need to think about applicable methods. The type of the method and solubility of the sample will govern analysis time, solvent consumption, and column selection. Lastly, you need to think about configuration and detection. In the first dimension, detection is optional. And for the second dimension, there is UV detection and ELSD available. Once you have completed this three-step process, you are ready to go to the lab and execute your plans. We hope that we triggered your interest in comprehensive 2D analysis on polymers. If you'd like to learn more about APC and WinGPC for 2D chromatography, there are some collateral available, as Ben already pointed out to. And the links have already been made available to you. This concludes the webinar. I would like to thank you all for joining us and following us on this comprehensive 2D chromatography journey. And I also would like to thank Ben and his team on behalf of RSC for facilitating this webinar. Finally, we are happy to take questions.
Thank you very much, Claudia, and thank you for joining us today. It's been a fascinating hour, very information dense. So anybody who's watched this almost certainly would benefit from going back and watching the recording again. You'll pick up a bit more because there was so much in the course of the last hour. We have overrun a little bit, but I think we should squeeze some questions in. So let's switch on our webcams so we can all see who's actually taking questions here. And seeing as she was the first person to speak in the presentation, let's go first with a question for Jenny. So Jenny, we had a question from Sergio. He said, what detectors does this work with? Can you couple in a mass spec? Probably a very common question. People looking at the equipment they've already got and working out how they can make it do that little bit more. Jenny, you're currently muted, I'm afraid.
Helps if I try again. So detectors. So our APC stack comes with ELSD detection, UTV, and PDA and RI as standard, like most GPC or LC systems. For 2D chromatography, some of those aren't compatible. So things like RI, because of the gradients that you would use in the first dimension when you're separating by chemistry, that is not compatible with RI. So largely we suggest either ELSD or PDA detection to go with 2D. Obviously that depends on your sample, so if it's not UV active, that'll have an impact on which detector you're using. And in terms of mass spec, polymer analysis in general, polymers tend to be a little bit too big for mass spec, generally speaking. And speaking for our mass specs personally, the solvents that the APC and the 2D system is compatible with generally would melt parts of a mass spec. So in some cases, mass spec analysis is possible for comprehensive polymer 2D analysis. We wouldn't really recommend hooking it up to a mass spec. I think that answers your question.
I hope so. Yeah, thank you, Sergio, for your question. There are still loads of questions we could get through. What we'll do, we will pass all of these questions on to Danny and Jenny and Claudia, and if they've got an answer for you, they'll be happy to email you with a response to that. So don't worry if we run out of time and we don't get to your question. Thank you for answering it. It is valued. We do appreciate it, and we'll try and get you an answer. Danny, let's look to the future. Are we expecting, having seen the advantages of 2D over one-dimensional, are we expecting any three-dimensional technologies in the coming years? And Danny, you are also muted, I'm afraid.
That is a really nice question. I like that one. Actually, we are already like kind of 3D because we have only shared with you the counterplots, which are really good to analyze data and to get numerical results. Actually, the colors, they also do have a meaning in these counterplots, and they reflect the concentration of each of the peaks that we have seen. So actually, we are kind of 3D already, and you can really make some nice pictures where you show the peaks with their different heights. Unfortunately, Jenny, I think we'll have to do, and Claudia, some work in the future, because I also agree to the first question that mass spec, at least for the lower molecular weight parts, would be a great addition. Not in the next years, next year definitely, but maybe in the next years. We'll promise to work on that, don't we?
Well, you're committed to it now. You said it on camera, so you'll have to do it now, I guess.
I know,
Claudia,
it's recorded.
No backing out.
Claudia, let's see if we can squeeze one quick question in for you, a fairly general one about the sorts of things you can detect. This is actually from Parvatalu, who's the same person who asked the future in 3D technologies question. So thank you for your questions, Parvatalu. Is it possible to detect polymeric products in petroleum products like corrosion inhibitors and so on? Is this the right sort of technology to use to detect the presence of those?
I'm inclined to say always yes, but it is you always have to do some method development upfront to see what you see eventually. If the based on the molecular weight, expected molecular weight range of the compounds, I'm always inclined to say yes. But it really depends on. I mean, I have not done it before. I mean, working on this particular on those particular compounds, but it should work. And it depends also a little bit on the column selection to see on how much you see and what you see.
Right. Well, thank you very much for the question, and we really have. I'm absolutely honoured and delighted that so many of you have stuck with us. We've only lost a handful of people, even though we're now, by my accounting, 13 minutes over the time that we originally said we would be. So thank you for sticking with us. Thank you ever so much, Daniela, Jenny, Claudia. Thank you for joining us. It's been a really interesting walk through a very complex, exciting area, and I do hope that everybody who's attended has got something from it. And we'll follow up with the resources that we've made available here, and also with the precision polymer analysis collection available on chemistryworld.com right now, which again was sponsored by Waters, who were very helpful in helping us to put this together. So thank you to Waters, thank you to our three speakers, thank you to my team in the background, Chris Pink, who has been helping us deal with all of your questions as well as keep things running very smoothly. So this has been a Chemistry World webinar. You will be able to find the recording. We'll send you a link to that in a couple of days' time, along with your certificate to say thank you. And do have a look at chemistryworld.com/webinars for other interactive events where you can meet the experts coming up soon. I'm Ben Valsler, Chemistry World's digital editor, and I shall see you again for the next Chemistry World webinar. Thank you.